an equation for which the greatest mathematicians of the past engage in heated debates and intellectual duels. This is the story of the cubic equation, a puzzle that challenged and inspired some of the most brilliant minds in history.
The origin of cubic solutions, a fundamental concept in algebra and mathematics, can be traced back to several ancient civilizations, with notable contributions from Babylonian, Greek, and Islamic mathematicians. Let's explore these contributions in detail. Let's embark on a journey through time, exploring the fundamental work of ancient mathematicians. Our story begins with the Babylonians, who thrived in the years 2000 to 300 BCE, and where they live is in modern-day Iraq, which is around here. The Babylonians were pioneers in the field of mathematics. They developed a sophisticated sexagesimal system, which is a base 16 numerical system. This enabled them to solve complex algebraic equations, including linear and quadratic equations. Among their numerous mathematical artifacts is the famed BM 13901, housed in the British Museum. This tablet, dating back to the Old Babylonian period, is a testament to their proficiency in mathematics, showcasing several problems leading to quadratic equations. Moving forward to Greeks and Romans, spanning from 800 to 600 AD, we encounter legendary figures like Euclid and Diophantus. These mathematicians laid the groundwork for mathematical developments. However, despite their profound contributions, they did not develop a general method for solving cubic equations. In fact, there is little evidence to suggest that Greeks and Romans understood completing the square in an algebraic sense, despite its geometric representation in their works. In the aftermath of the Roman Empire's fall, China entered a golden age of mathematical exploration. The era's most eminent figure, Wang Xiaotong, authored the Jigu Suanjing, a treatise that revolutionized the understanding of cubic equations in the East. Wang's methodical approach was not just about solving equations. It was about understanding the complexities of the real world through mathematics. Let's delve into an example from Wang's treatise. Wang Xiaotong sets a scenario for constructing a dike with varying dimensions. The challenge involves calculating the labor required, considering the workforce from different counties and their daily digging, carrying, and building rates. In order to solve this, Wang composed a quadratic and two cubic equations, albeit not all algebraically, with both cubic equations in the form of ax to the power of 3 plus bx to the power of 2 plus cx equals d, where a, b, c, and d are all real, non-zero constants. Wang Xiaotong's approach to solving these equations was primarily numerical. He applied a detailed and methodical process to find the roots of these equations. While the primary influences of Wang Xiaotong's work was within China, his methods and solutions contributed to the overall global development of mathematical thought, particularly in polynomial solutions. Moving forward in time, we reach the Islamic Golden Age, spanning from the 9th to the 14th century. This period saw unprecedented advancements in various fields, including mathematics. Among the mathematicians in this period, two stands out: Al-Khwarizmi and Omar Khayyam. Al-Khwarizmi, often called the father of algebra, introduced the term in his seminal work, Al-Kitab al-Mukhtasar fi Hisab al-Yabr wal-Mukhahala. His approach of completing the square laid the foundation for solving quadratic equations, which later influenced the solutions of cubic equations. Omar Khayyam, a Persian polymath, made significant strides in solving cubic equations. In his treatise on algebra, he classifies cubic equations into several types and provides geometric solutions for each. For instance, consider the equation x to the power of 3 equals ax plus b. Khayyam solved this by constructing a parabola and a hyperbola, finding the solution at their intersection. Omar Khayyam's methods marked a pivotal moment in mathematical discovery. The Islamic world now sets the basis for further discoveries in Renaissance Europe.
Scipione de Ferro was born in Bologna, Italy, in 1465, and he was a professor of mathematics in the University of Bologna. He was interested in algebra, geometry, and astronomy. He also participated in mathematical contests, which were very popular at that time. He also challenged other mathematicians to solve problems and won. One of the problems that de Ferro was able to solve was the depressed cubic equations. He discovered a formula that could find the value of these equations. These equations are quite complicated, but it works for any depressed cubic equation. However, de Ferro did not publish his formula or share it with anyone. He kept it as a secret until his deathbed, where he told it to his own student, Antonio Fior. Fior was born in Venice, Italy, in 1499, and he was a lawyer and a mathematician, and he learned the formula for the depressed cubic equations from de Ferro. He also participated in many mathematical contests, and the most important thing was he challenged another mathematician, Niccolo Tartaglia, to solve 30 depressed cubic equations. Tartaglia was able to solve all 30 questions using his own method that he had discovered independently from de Ferro. Tartaglia did not reveal his own method to Fior, but other mathematicians like Cardano, who we will mention later, eventually decoded his solution. More on that later.
In mathematical history, few stories are as intriguing and dramatic as the rivalry between Cardano and Tartaglia. Today, we'll delve into the life of these two mathematical giants and the fierce competition that defined their legacies. Our story begins in Pavia, Lombardy, with the birth of Cardano on September 24, 1501, son of a lawyer mathematician father and a poor widow. Cardano's early life was marked by illness, a difficult relationship with his father, and an almost fatal birth. Interestingly, his father was a friend of a great Leonardo da Vinci. Cardano was a student of philosophy and science, earning his medical degree from the University of Padua in 1526. He moved to Milan, where he gained renown as a lecturer in mathematics and as a successful physician. Despite his professional achievements, Cardano's life was rife with controversy, from accusation of heresy to personal tragedies, including the accusation of his son. In his later years, after being released from accusations of heresy but losing his position and right to publish, Cardano spent his final days in Rome, passing away in September 21, 1576. Now let's turn to Tartaglia, born in Brescia around 1499. Tartaglia, meaning Strammerer, a nickname he adopted after a sabre wounded his face, was largely self-taught in mathematics. He gained his fame as a teacher in Venice and for his contributions to various mathematical fields.
And now we're gonna talk about Lodovico Ferrari. Ferrari was born in the 16th century Italy, and at that time Italy was not a unified state, and instead it was a set of city-states. And these city-states often engaged in political conflicts, and they were also influenced by outside forces, such as the French Empire and the Spanish Empire. And Ferrari's grandfather Bartolomeo was persecuted politically, so he and his family traveled to Bologna, Italy. And in Bologna, Ferrari's father died when Ferrari was very young. So Ferrari was raised up by his uncle Vincent. And Vincent had a son named Luke. And Luke worked for the mathematician we previously talked about, Cardano. But Luke just did housework for Cardano, really simple tasks. And Luke found the job very boring, so Luke ran home. And yet his service with Cardano didn't end yet, so Cardano commanded Vincent to send his son back to work with him. And Vincent wanted to protect his son, so instead he sent his nephew, he sent Ferrari to Cardano. And Cardano quickly discovered Ferrari's talent, and it would be a waste if Ferrari keep doing simple houseworks. So Cardano taught Ferrari how to write, how to read, how to do mathematics, and Ferrari began to organize manuscripts for Cardano. And they were no longer master and slave, but now they're teacher and students. And this is how Ferrari will become a future genius. And together, Ferrari and Cardano made many significant improvements in mathematics. And Cardano was informed about the solution to depressed cubes. And then he geniusly figured out a way to expand the formula for depressed cubes to all kinds of cubic equations. So now Cardano can solve every cubic equation with every term involved. And Ferrari subsequently used the formula from his teacher to solve the quartic equation. And the solution, the mathematics behind the solution, we will explain it later. Now let's look at this quartic equation. To solve this, an idea is to complete the square on both sides, so we can take the square root simultaneously, and I'll show you how to do it. And first, let's add some terms on both sides. As you can see, we complete the square on the left side, and this can be rewritten as, and we rearrange the terms here. Now we want to select a value of b, so that the right side is also a complete square. And we can do so by calculating the discriminant of the right side. If the discriminant is 0, then we can safely say that the right side is also a complete square. What's the discriminant? It's b squared minus 4ac. And that would be 12 squared minus 4 times 2b times b squared minus 3. And this can be simplified as 144 minus 8b cubed plus 24b. And we want this term to be equal to 0. And how can we solve that? Well, fortunately, Ferrari and Cardano know how to solve this depressed cube. And as you can see here, this is just another equation of depressed cube. And Ferrari and Cardano can confidently solve that b is equal to 3. And then we can plug in b equal to 3 back to this equation. And we can now rewrite it as x squared plus 3 squared is equal to b is equal to 3, 6 x squared plus 12x plus 9 minus 3, which is 6. And look, we can factorize the right side as x squared 6 times x squared plus 2x plus 1, which is a complete square. Well, we move these down. And this is this is another important step, which is to take square root on both sides. Plus 3 is equal to square root of 6 plus minus square root of 6 x plus 1. And look, this is just a quadratic equation, and anyone who passed 8th grade know how to solve this. So Ferrari convert a nasty quartic equation into an easily solvable quadratic equation, and that's the Ferrari method of solving the quartic equation.
Embarked on a journey through time and intellect as we unravel the life of Paolo Ruffini, a mathematician who braved the tides of intellectual duels to shape the course of algebra. Paolo Ruffini was an influential Italian mathematician and philosopher. Born on September 22, 1765, in Valentano, his contribution to mathematics, particularly in the field of algebra, was highly regarded. Ruffini's early education was in a seminary, and he later studied at the University of Modena, where he showed a remarkable aptitude for the mathematics and philosophy. Ruffini's work spanned various areas, but he is most famous for his contributions to the theory of equations. In 1799, he made a significant attempt to prove the impossibility of solving general polynomial equations of degree higher than 4 by radicals, a topic that was fully resolved later by Abel and Galois. His work in the area laid the groundwork for the development of group theory, a fundamental area in modern algebra.
Now I'll do a demonstration of how to use the Ruffini's rule. For example, we have a cubic equation here, x cubed plus 3x squared minus 10, and we need to test if x equal to 2 is a root of this cubic equation. And Ruffini's method is basically long division, and I'll show you how to do it. Firstly, let's write down all the coefficients, 1, 3, 0, and minus 10. And now we'll test if 2 is a root. So we put 2 here. The first coefficient, let's just drag it down, 1. And then 2 times 1 is 2. We put plus 2 here. 3 plus 2 is 5. 5 here. 2 times 5 is plus 10. We put plus 10 here. 0 plus 10 is plus 10. Just put 10. And then 2 times 10 is 20. Put 20 here. 20 minus 10 is 10. Now we have finished this long division process. And the next step is to use these coefficients. We have 1 here, so let's write down x squared. And then 5 here, 5x, 10 here, 10. And for the final 10, it's a constant, so we put 10 divided by x minus 2. And this is the solution to this fraction. And because there's still a remainder here, 10, we can know that x equals to 2 is not a root to this cubic equation. And this is the Ruffini's method. As you can see in the previous demonstration of Ruffini's method, it's not just a solution for cubic equations, but it can be applied to all orders of polynomials, quartic, quintic. And actually, Ruffini is the first to point out that a quintic equation does not exist. We have quadratic equation, cubic equation that can give us all the roots to any quadratics, any cubics, but a simple equation does not exist for quintics. Ruffini tried to prove this, but he's on the right track about permutation of roots, but he did not finish the proof. His work was not conclusive, and it was rather his contemporary Galois and Abel who finished the work. Galois first proved that there's no general equation with radicals to solve the quintic equations, and Abel further expanded the concept of group and connected with polynomials to prove that beyond the quintet equation, a general solution does not exist.
The role of conflict is nowhere from negligible on the road to the eventual discovery of the cubic equations. Looking back to this history, it might as well be appropriate for us to digress now and try to evaluate the effect of these conflicts on the history of mathematics and humanity as a whole. The examination of historical conflicts among prominent mathematicians, such as those between Cardano, Tartaglia, and Ferrari regarding the cubic equation, and between Newton and Leibniz over calculus, reveals how personal animosities and rivalries between a few great minds can detrimentally impact the progression and sharing of mathematical knowledge. The conflict between Cardano and Tartaglia over solving the cubic equations reveal the darker side of an academic pursuit, the ethical dilemmas and breaches of trust driven by the desire to recognition and fame. This rivalry not only soured personal relationships, but also created a competitive atmosphere that may have hindered open collaboration and the sharing of ideas within their mathematical community. The dispute between Tartaglia, Ferrari, Cardano further exemplifies the negative impact. Their public debate, though intellectually stimulating, was tarnished by public personal attacks and ego-driven arguments, overshadowing the mathematical concept. Such conflicts, while they may inspire a rigorous defense of mathematical ideas, can devolve into unproductive confrontations. As we reflect on these historical incidents, it becomes clear that while competition and the desire for recognition are nature human tendencies, they can lead to divisions and hinder the collaborative spirit. Understanding these past conflicts offer valuable lessons for today's academic community. It underscores the importance of maintaining professional ethics, fostering an open communication, and prioritizing the collective pursuit of knowledge over individual accolades.
我开了，
我也开了。
干。
开。
干。
So after Ferrari won the debate,
录一下，前面伸个舌头，模仿一下。
脑瘫没有徐芳那么恶心。
哦天哪，姚然，拍下鼻孔。